Hello, my name is Kelly, and today I'll be sharing my findings from Lab 4, Circuits. So this lab aims to demonstrate how circuits work by measuring potential difference within the circuit and analyzing the relationship between resistors in the form of light bulbs and capacitors in order to determine an RC value. I accomplished this by modeling circuits in Colorado FET's circuit construction kit and using their built-in voltmeter, ammeter, and stopwatch tools to take measurements. Some guiding principles include the node rule, which says that the sum of currents going into a node equals the sum of currents going out, and the loop rule, which says that the sum of the potential differences within a loop in a circuit equals 0. Finally, Ohm's law, which describes the relationship between resistance, current, and voltage. Additionally, to understand the relationship between resistors and capacitors, we know that the discharge of a capacitor follows exponential decay. So taking the natural log of this relationship gives us a plot that can help us determine our RC value, which is the time at which the voltage difference has dropped to 1 over E of its original value. For my results, I found my RC value to be 5.9 seconds. So after I downloaded the circuit construction kit, I constructed a circuit with two 1.5 volt batteries in series to give a total of 3 volts, connected to 2 resistors, one at 47 ohms and one at 100 ohms. Following Ohm's law and the node rule, I expected the circuit to follow the equation current equals voltage over resistance, giving me a predicted value of 0.204 amps for both ammeters. I found that the ammeter readings were independent of how they were hooked up, as they're shown in reverse on the right. When we break up the circuit and measure the potential difference, we see that it's the same as the EMF, because the series is open and the voltmeter doesn't allow current to flow through. To measure the round-trip potential difference, we add up the individual potential differences of segments across the circuit, and the sum of the potential differences in the closed loop is expected to be 0 due to the loop rule. Plotting the voltages as we traverse the circuit, we see that the net voltage across the loop is 0. This satisfies the loop rule. And from this, we can confirm the resistance of the resistors and the lack of resistance in the ammeter and wires using Ohm's law. Finally, adding an ammeter in parallel with the 100 ohm resistor increases the current of the circuit because the electrons flow freely through the ammeter route since there is no resistance there. To make the RC circuit, I connected a 9V battery, 10 and 20 ohm light bulb, and a 0.2 farad capacitor. Looking at my RC circuit, the 10 ohm bulb was initially bright, but as the capacitor is charged, it dimmed. Removing the battery and completing the circuit let the capacitor discharge with the same bulb effect and time as charging. This result was consistent with the 20 ohm bulb with almost double the time of the 10 ohm bulb. Using a 30 ohm bulb, I recharged the capacitor and set a voltmeter across the capacitor. I also timed the discharge and recorded voltages. Using the natural log equation on the right, I plotted natural log of delta V over delta V naught versus time to get a line of best fit, whose slope is the inverse of the RC value, which I determined to be about 5.9 seconds. To end, if I used a real ammeter, since actual ammeters have some resistance compared to the 0 ohm resistance of my ideal ammeters, they would actually read lower current than what I observed in this simulation. And if we used real batteries and capacitors, we would be adding additional factors into this lab, such as the internal resistance of the battery and capacitor, which makes the charging of the capacitor slower. Thank you for watching.